All right, so it always is a hard act to follow after Ari, but Ari gave you a little bit of this introduction. This is one of the efforts that we're really putting in a lot of effort. And I'll mention it's not only, it's already a big team, but I mentioned a lot of what I'm going to talk about here briefly in this first few slides would not be possible without an even bigger effort by a lot of folks involved. Some of you are here, which is on the National Science Foundation 10-story tall wood design project that's being led by Shilling Pei. So I want to acknowledge that before I get into this. We have two projects that are currently funding our efforts on the 10-story and then a 6-story project that will follow. And as Ari was showcasing, so in 2017, there was already a collaboration between Tallwood and the team that's leading, there in blue, the NSF Tallwood team led by Shilling Pei. That was in 2017. We had a 2-story building structure that was built and designed, I would say almost in record time, because in January 2017, we were down in in Chile at the World Conference of Earthquake Engineering. And between then and May 2017, we were already receiving panels on the shake table site. So for all of those of you that do projects and work on design, you know that that's an amazing timeline, especially today where we are with supply chain. I don't know if we would have been able to do it. But with that said, it was a fantastic experience. This was shaking just in one direction because at the time the shake table would only do shaking in one direction, and we had 2 rocking systems. And our contribution, the special contribution from Tallwood, was actually looking at the diaphragm. So we had, at this story, we had CLT only diaphragm, and on the roof, we had a composite system based on some testing that we had done here a couple of years ago, before that, looking at CLT plus concrete. Ari talked about the 3-story building. So this year, in November 15, that's, as Ari announced, we're going to have the first test there. And then the 10-story project, I could not do justice to all the work that Ling and his team have put in, and big numbers. This is currently at around $3 million of donations, time, and materials that has been put in already into this building. And so it's a huge effort that the wood community, right, is contributing to. And I really want to acknowledge that. So where we come in is also to try to help, even with the 10-story, making that a success. We looked at opportunities to do additional testing. And one of the opportunities, because on a shake table, we do have to demolish the building. So we're going to start and we're going to demolish 4 stories. Even yesterday, folks with Timber Lab that are up here, we were discussing how do we actually make this work and how do we actually make this work safely as well. But we're going to take out 4 stories. We'll be left with a 6-story building. And then we're going to have 2 main phases are confirmed right now. Phase 1, where we will swap out what our energy dissipation devices. And then phase 2, we're actually swapping out walls, 6-story wall panels that will swap out and bring in new wall panels. And for each of those phases, we'll add instrumentation and do the shaking test. And so that's the focus of the 6-story. There's contribution from the National Science Foundation. There, we're working on a design methodology that accounts for sustainability and accounts also for functional recovery. And then there's also funding from USDA that's specifically looking at reuse. And so that's what Tallwood and the USDA-ARS is helping us fund. So we have confirmed 2 wall solutions. The wall solutions stem from what Ari was showing us here just before. So one has UFPs. Ari said it was standard. I wouldn't quite call it standard yet, but it is a solution that's been out there, and we have it in PV Hall as well. And you'll see it if you make it to Emerson. And then there's a solution with BRBs that was used, original concept was actually used in the catalyst building. Here we're using post-tensioning as well, and not on the ELLI, but on the 6-story, we'll be using post-tensioning. And for the BRB solution, her name was up, but Barb Simpson and Gustavo in the back have actually been the ones doing all the design work for that phase. Main takeaways, it is seeming possible, we still have to actually make it work, that we will be able to reuse the specimen. I've mentioned, but this wouldn't be possible with great collaborations across teams and across academic industry partners and leveraging large projects. Collaboration and trust, you need to build that trust both in terms of academics, but also with industry partners. We're not doing something that's done every day. So there's a lot of meetings, a lot of discussions, but that trust is key in order to work together. And also because we're promoting the use of wood and everybody's looking at what we're doing, right? But then we are looking at this opportunity for reuse. So that's where tall wood comes in, and collaboration with the University of Oregon, Judith Shine and Mark. I saw Mark there as well. Yeah. And so there, what we're doing is, as we are going to deconstruct this building, and to make this building possible, I've listed here all the different acronyms, and I don't think I could come up with any more acronyms today on what mass timber panels we have available. But that the building has multiple materials at multiple floor levels, so opportunities to look at what are potential reuse for each of those systems. And as part of that, we are doing LCA analysis, and we are also looking at how those materials can be reused. Very generic, there hasn't been any such study. There's been one reuse project that we found, which was actually in Japan, and Passarelli looked at reuse of a building that was tested on the shake table in Japan, and that was deconstructed, and they did a small cafe. Some panels were used for a small cafe in Kobe, Japan. But other than that, there hasn't been, and also in terms of reuse of mass timber elements, there isn't a lot of information out there. Long, boring slide, but we have multiple tasks in this project. But ultimately, we're looking at two buildings, both the ELLI and the Tallwood building. And there's a poster out there in the back where you can spend more time looking at more details. But this is work done by Amanda Stanton and Judith Shine, where for the ELLI building, if anybody has a chance to go to the Emerson Lab today, you'll have a chance to look at it closely. But we've done an initial study. Amanda and Judith have done an initial study where we're looking at potential reuse of the panels, thinking about how we can cut them up, what are areas of the panels that can be reused, and then when possible, looking at solutions for upcycling the material. So maybe you have panels that can be reused as panels, but maybe those panels can be cut into beams or columns. And for example, working with folks that have developed this new product, Boise Cascade, which is mainly 4-foot, they said, oh yeah, you could probably cut those up and use those for columns, for example. And it would be a lower grade, not typically the grade that we like to sell most, but it would be a grade for columns that could also be used. So looking at opportunities for reuse of those materials. So that's a quick update on what we're doing on the shake table and the ELLI project. And then Evan asked that I also present other work that we finished recently, the testing, and we're still working on finalizing and journal papers and work. So I'm shifting gears a little bit from the shake table testing to structural design and testing of a composite system. Now I'm talking about concrete mass timber panels. Specifically here, these mass timber panel solutions are using MPP. But some work had been done before. We started thinking, what if we add acoustic layers between the concrete and the mass timber panels? And that's what this work is on. So timber concrete composites, there's several advantages. You improve response for gravity, seismic, and also you have better fire performance by adding the concrete layer that in most types of constructions, you need to have at least 1 inch there of some gypcrete or concrete. It improves acoustic and vibration properties if you have with the added materials. It lends itself to prefabrication. You can reduce the corresponding depth of a CLT only slab would be larger than if you're using a composite system, and you can improve other performances. But if you think just concrete slab solution, you can add also the mass timber part to it, so improving in terms of global warming potential. These concrete slabs can be cast in the field, on site, or in a precast environment. I haven't seen any solutions in the US where that has been done precast, but in Europe, there's a couple of startups that are doing that and actually develop this in the shop, the composite system, and then a lot more crane, a lot more work to actually put up in the building, but that's a composite system that works for that. Usually on site is preferred, but there have been concerns. And last week was in something organized by Woodworks, and there was some discussion by folks from Turner and others that there's concerns about construction hazards, right? If you're doing composite and you have screws or plates that I'll show you next sticking out of the slab, that lends itself to some construction hazards, and also the sequencing in terms of when do you cast the concrete? Do you close out the building? Do you come back and then pour the slab? Do you pour the slab and then slow the construction because you have to wait for concrete to cure? So there's pros and cons about these solutions. I listed many more pros, but there are cons and things to think about as well when you're actually trying to use them. Thinking specifically about the acoustic performance, there's been some work, by Woodworks, and Ian McDonald collected, and TDI collected a series of tested solutions. I believe most of them tested with University of Oregon, but where you looked at different layups here in terms of you have mass timber, and for example here, I'm sure in the back you can't see this, but there's an acoustic mat and there's a 3-inch concrete layer. So this is a solution that has an STC of 53 and an IIC of 45, where according to building code for multifamily housing, it's indicated that you should have IIC of 50 and STC of 50. So that's getting close to that, but not quite. So you'd still need, if you're looking at IIC, you'd need additional acoustic layer or something else to add in performance for that IIC. And if you look here at the bottom, this is a composite solution, such as we've thinking purely structurally, where you have 5-ply CLT and you have 2¼ concrete thickness, and there you get an STC of 49, but the IIC is 19, way below what would be needed. So you do need an acoustic mat above, below, to make that work. And so that's where we started thinking, what if we add it in the middle? We weren't the first ones to think, what if we added in between the concrete and the wood? There's been some work in Europe, and purely thinking structurally, you started seeing that there was reduction of strength and reduction of stiffness if you add that element in between the concrete and the wood. So with that, we decided to look at characterizing what is the slip modulus, key design parameter, and what's the stiffness and what's the strength of these systems, in this case using MPP and reinforced concrete. And when we started doing this work, it was either screws or a mesh, epoxy steel mesh that were the typical solutions that were out there available. So we looked at both in our testing. And then we looked not only at one-way bending, most of these solutions are under one-way bending, but there are cases when you have to look at two-way bending as well. So looked at two-way bending, stiffness, what we're calling here elastic orthotropic, but it's two-way bending stiffnesses, and also warping, so what you do to design slabs. MPP with 3-inch, so 4-inch MPP, 3-inch reinforced concrete, that was the solution. We looked at screws at 45 degrees and 90 degrees. We looked at epoxy mesh, steel mesh, And we looked at insulation thicknesses. This on the left is a product by Rotoblast. It's only 0.2 inch, 5 millimeter. And on the right, it's Maxon, a 3/4 inch thickness, 3/4 inch mat there, acoustic mat. We started by doing some push-off tests. It looks like this. You have a concrete layer and you have the MPP and you push on the concrete and you measure the displacements across the interface. And jumping straight to results in the interest of time, on this axis is applied load, and here are different configurations. The first three are with screws at 45 degrees. The next three are with screws at 90 degrees. And you see that as you go from 0.5 to 19 mm insulation thickness, you have a reduction on the push-off test. You have this reduction of strength. That's the average value, and that's the swing of our outputs in terms of maximum and minimum values that were observed. And similarly at 90 degrees, a little bit lower strength, and a reduction as well as you increase the thickness there. We had done some testing led by Chris. Sorry, not this one, was actually in Europe and with Rotoblast and with different screws, but similar solution with similar density of wood, and the results were, in the same ballpark. The dashed lines are other literature results without insulation and with insulation, with a 5 millimeter insulation as well. So with MPP, we're getting a little bit stronger, but similar capacities. In terms of slip modulus, that's important to characterize the stiffness. There's a much bigger effect of S0 is without any insulation, S2, S3 is with 5 mm and 19 mm insulation. So there's a large effect of, especially in the slip modulus, of the interface layer. But if you look at the 90 degrees as well. So especially from this push-off tests, we saw a little bit of reduction of strength, but significant reduction of the slip modulus as expected. You're adding a layer that has no stiffness in between the concrete and the timber. When you get to the HPV mesh, sorry, this was not HPV mesh. I keep saying it's HPV, but it's not. It's just an epoxy steel mesh. We looked at 3 different embedment depths, 1.25, 1.5, and 1.75. And there, in terms of load, you don't see as much of a decrease or minimal decrease in terms of load. In terms of percentage, it was much smaller. And each of these columns, again, E1, E2, E3 are E1 is no insulation, E2 is 5 mm, and E3 is 19 mm insulation. So especially here, you see that it's within the errors there in terms of that variability, but a little bit, but not a significant reduction in strength, and also not as significant. There's some, but as you increase the thickness of the insulation, you don't see considerable decrease in the stiffness when you have the HPV mesh. So your epoxy steel mesh is engaging much more into the concrete and the wood, and that gap in the middle is not as effective in reducing the strength and the stiffness when you have that rather than the screws. We moved on then to test this in bending. There's only so much you can learn just from the push-off tests. And when we went into bending, we did simple, so one-way bending first, and jumping also to the results. First of all, there's a new case here on the left. This is just the MPP. So you have a reference of what just the MPP is giving in terms of strength. And then the columns, there's a lot of information here. You have first just the screws and then the 3 different depths of the steel epoxy mesh. With the screws, we saw again a reduction in strength overall, but not with the mesh. Okay, so again, with these different thicknesses of insulation, so no insulation, 5 mm and 19 mm insulation, we did not see a decrease in strength as you add the interface layer in between. When you look at the stiffness, screws, there is still a reduction. And interestingly enough, you actually see an increase in stiffness there when you add the insulation layer. And when we looked at this, we thought, uh-oh, we have a problem. We have a mistake. And we kept scratching our heads. And then we went back to basics. And what happens is we're adding insulation layer. So the overall thickness of the slab is actually increasing. And as the thickness of the slab increases, you actually add additional stiffness to the system. And so that's why as you add the insulation layer in between, as you go from 0.5 to 19 mm, you actually have a deeper section overall with the insulation mat already there. And that's what's making this increase in stiffness across the board. So that was an interesting result. When we talked to the folks providing the mesh, they said, "Oh yeah, we knew that was going to happen." I was like, "No, why did I scratch my head for so long?" But it was interesting to see. One thing that I also want to point out here is in terms of stiffness. So we had done series of tests in 2015 and 16 where we looked at CLT plus 2¼ concrete cover, and we looked at HPV mesh and screws. And this dashed line is 5-ply CLT plus 2¼ concrete. So total almost 9-inch slab solution with the MPP using 4-inch plus 3-inch of concrete. We get the similar stiffness. The strength is a little bit lower with the 7-inch solution versus a 9-inch solution of CLT plus 2¼ but the stiffness is similar without the insulation layers, and then it actually increases. So this was also, double checking that our results were making sense. For the two-way bending tests, you see anything weird in this test? It's upside down. So we're looking at positive bending and negative bending as well. So we're looking at both. This was the case when we're looking at negative bending. And we looked, thus we can estimate parameters that we use for slabs. So the stiffness in the positive in both directions, X and Y, and in the negative as well. So we were able to characterize what those were. Here, it was just with no insulation. So these are just to provide those numbers. And then we can have, based on the one-way bending test, we can get estimates of what that offset would be with insulation layer, but we did not test with insulation layers as well. And this one is a really cool test. This is Chris Higgins setup out in Hinsdale, where we're doing warping testing. We put weights on this corner and we check how much that slab is actually warping. And we can come up with the warping factors also for use in design, which if you are trying to model shells in most of the software that we use in structural engineering, these are also useful to have to get better predictions of what those are. In the end, just to summarize, we did the shear test, the push-off tests, and we saw strength and stiffness decrease for both, but less in the epoxied steel mesh and more as you had screws at 45 degrees or 90. There were no notable differences. I didn't even touch that, but we had 3 different embedment depths for the steel mesh, 1¼ through 1 3/4, and 1¼ worked fine and got the same. There was no notable differences for those 3 levels of embedment tests that we looked at. For the bending tests, there was reduction of strength and stiffness observed for the screws when we added the interface layer. And then for the epoxied mesh, there was no reduction in strength, but it was actually an increase in the stiffness, as I mentioned. And then in terms of warping, I didn't touch base, but we can share the slides. They were very similar results for both tests there. Acoustic testing is needed. We only did structural testing for these. So especially for the IIC number that I had mentioned, that's one key one to look at. And there's a follow-on project that our colleagues here will talk about later, and also long-term performance. And then we've done some analytical work, so using gamma method and another method to try to estimate what is the effect so that engineers can do the calculations based on what we've learned. So we're still working on that, but that's going to be part of the journal publication that we're coming up with. And that's it. Thanks.